Pause right here, read it properly, and lock in your answer. Otherwise, 5 seconds, and then I'll show you the correct option and walk you through the whole concept. It's A. The default is a range frame, and that one word is the difference between the number you wanted and the number you got. Let me show you. An order by already chose your window frame. Here are 8 payments for one customer, ordered by event time. Watch rows 2 and 3, they share the same timestamp. Now the running sum, with no frame specified at all. Range is the default, and range is value-based. Every row sharing the current row's event time sits inside the same frame. So both 905 rows read 200. 150 never happens. Ask for rows explicitly, and it does. Rows counts positions, not values, so the second row closes at 150. Same data, same ordering, different frame. And a real last 7 rows window? That's rows between -6 and 0. Watch the top edge move. Row 8 arrives, row 1 drops out, and 840 becomes 740. Pause here, read it carefully, and commit to an answer. Otherwise, 5 seconds, and then I'll reveal the correct option and show you exactly what's going on. It's C. The checkpoint is the stream's memory, and it outranks the option you wrote in your code. Let me show you. Starting offsets is read once. The checkpoint is read every time. Here's a topic with 10 events, offsets 0 through 9, and a stream that asks for earliest. First start, the checkpoint is empty, so earliest is honored. All 10 events come through, and the checkpoint writes down where the stream stopped. 3 more events land. Restart, same checkpoint. Spark doesn't even glance at starting offsets now. It opens the checkpoint, reads resume at 10, and processes exactly the 3 new events. No replay. Now the redeploy that caused the incident. Same code, same topic, but a fresh checkpoint path. An empty checkpoint means a brand new query, and a brand new query honors earliest again. All 13 events, reprocessed. So the fix isn't an option, it's an address. Keep one persistent checkpoint location, and every restart resumes exactly where the stream left off. 500 gigabytes on one side, 2 on the other, and somehow, the whole thing is shuffling. Read the profile carefully, pause, and pick your diagnosis. 5 seconds, then I'll show you what the optimizer was actually thinking. It's B. The optimizer never saw how small that lookup really was, so it refused to broadcast and shuffled half a terabyte instead. A small table should travel. A big one should stay put. Here's the join. Transactions on the left, product catalog on the right. Sort merge join means both sides get shuffled. Every row of that 500 gigabyte fact table crosses the network to meet its partner. That's the cost you saw in the profile. And those 3 8-minute tasks? Hotkeys. A few products own most of the rows, and whoever gets those partitions drags the whole stage. Now the fix. Tell the optimizer what the lookup really is, a broadcast hint, or fresh statistics from analyzed table. Watch the plan flip. The little table ships to every executor, and the fact table never moves. Our scaled down run, 3.2 seconds becomes 0.8. Then, enable adaptive skew join, and Spark splits the hot partitions at runtime. 2 fixes. 1 kills the shuffle, 1 kills the stragglers. You ran the delete. You ran the vacuum. The auditor says the data is still there. Pause, think it through, and commit to an answer. 5 seconds. Then we'll open up the files and look. It's C. With deletion vectors, delete is a bookmark, not an eraser. The bytes are still sitting in the Parquet file. Let me show you. With deletion vectors, delete is a bookmark, not an eraser. 6 users. We delete user 42, and select agrees they're gone. But look at the files, the same 4 Parquet files as before. The delete just wrote one tiny bitmap on the side. This row in this file is dead. That's why it was fast. Nothing was rewritten. Now the auditor opens the Parquet file directly. There's Amara. name, email, everything, still physically on disk. And vacuum? It removes old unreferenced files. These files are current. It removes nothing. The purge is a three-step dance. Reorg table, apply purge. That actually rewrites the affected files without the dead rows. Then vacuum sweeps away the old copies. After both, user 42 appears in 0 files. The source only touches 7 days of data, but the merge reads the whole table, and it gets slower every single week. Pause and pick your fix. 5 seconds, then I'll show you where all that time goes. It's A. The merge scans everything you don't rule out. Put the 7 days into the condition, and the search space collapses. Let me show you. A merge scans everything you don't rule out. The target, 60 daily partitions, 1.2 million rows. The source, 35,000 changed rows, all from the last 7 days. But the merge condition only says event IDs must match. So to find those matches, Delta has to consider every partition, all 60, every night. And the table keeps growing. Add 1 line to the condition, target event date within the last 7 days. Now partition pruning goes to work. 53 partitions eliminated before a single byte is read. 7 scanned. Same merge, same 35,000 rows updated. In our run, the scan dropped from 6 seconds to 2. The whole merge from 8 to 3.5. And the real win? The cost now tracks the 7 days you touch, not the size of the table. 500 million rows through 1 Python function. One of these 4 works. 1 explodes. 2 just crawl. Pause and choose. 5 seconds, and then we race them. It's E. The pandas UDF doesn't cross the Python border row by row. Arrow carries whole columns across in batches. Let me show you. 500 million rows through Python. The border crossing is the whole game. The logic has to be Python. It calls an encryption library. The question is how data reaches it. A standard UDF sends rows one at a time. Serialize the value, cross the process boundary, run the function, ship the answer back. Per row. Watch the meter. 38,000 rows a second. At that pace, 500 million rows takes hours. The pandas UDF changes the transport, not the logic. Apache Arrow packs the column into batches of 10,000, 1 crossing per batch, and Python receives a whole series. Same function, same pipe, 900,000 rows a second. 24 times faster in our run. 2 pandas would drag everything onto the driver. Built-ins can't call your library. 1 wrong parameter took the rundown, and half the tasks already succeeded. You need surgical precision here. Pause, lock in your answer. 5 seconds, then I'll walk the repair. It's D. Repair run reruns only what failed, and the parameter override lives and dies with that 1 repair. 1 bad parameter should not cost you the whole pipeline. Here's the run. 5 tasks. Ingest and validate already succeeded. Then transform read env equals staging connected to the wrong source and failed. Load and publish never got their turn. The instinct is to fix the job and run it again. But look at what that actually means. Rerunning work that already succeeded, and changing a default that every future run will inherit. Repair run is the surgical option. Open the failed run, choose repair, and override env to production. Right there in the dialog. That override applies to this repair only. The job definition keeps its original defaults. And watch what reruns. Transform, load, publish. Ingest and validate keep their results. No waste in compute. 1 run record, and the job definition never changed. The grant is there. The table isn't. The analyst can't even see it in the browser. Something above the table is closed. Pause and choose. 5 seconds. Then we walk the hallway together. It's B. Select is a last lock, not the first. Unity Catalog makes you open the catalog and the schema before the table exists for you at all. In Unity Catalog, select is the last lock, not the first. Think of the table's full name as a hallway: catalog, schema, table, finance, reports, revenue. 3 doors, and every door has its own key. Our analyst holds the table key, select, but no key to the catalog door. And Unity Catalog doesn't just refuse the query, it won't even admit the table exists. That's why the browser shows nothing. Grant use catalog on finance. The first door opens. Grant use schema on finance.reports. The second one. Now the select grant finally has something to unlock, and the query runs. So remember the shape. Every parent on the path needs its traversal privilege. One missing key anywhere in the hallway, and the grant at the end of it is worthless. More rows today than last week, and nobody sent anything. Is the provider pushing? Is the share stale? Pause and commit to an answer. 5 seconds, then I'll show you how the share actually moves. It's E. Nothing is pushed, nothing is copied. Every query is a live pull of the latest committed state, and the share itself can be a streaming source. Let me show you. Delta sharing doesn't push data. It lets the recipient read. Here's the provider's orders table, and the share is just a pointer to it, with permissions attached. Last week, the recipient queried it. 8 rows. That query read the provider's current committed state directly. Nothing was copied. This week, the provider committed 5 more orders. The recipient runs the same query, 13. Not because anything was sent, the pull simply saw newer commits. That's the whole model. Every query is a live read of the latest committed table, and incremental consumption is built in. Point-structured streaming at the share. The first pass reads everything, 13, and writes a checkpoint. 4 new orders land, and the next pass reads exactly those 4. With history sharing enabled on the provider side, the share itself is a streaming source. Last one, and it looks easy. Your alert just went triggered. Careful, 3 of these 4 read exactly how you'd guess wrong. Pause, 5 seconds, and then we close this out. It's D-triggered, means the alert worked. The query ran, and your condition came back true. Let me show you the whole state machine. An alert status is a verdict, not a health check. Here's the state machine. Every scheduled run does 2 things: execute the query, then test the condition. Monday, the null count comes back 3. The threshold is 5. Condition false, status okay. Tuesday, a bad batch lands. Null count 9. The query worked perfectly, and the condition is true. That's triggered. And because the state changed into triggered, the notification fires. This is the alert succeeding, not failing. Wednesday, someone breaks the query, a typoed column name. It can't even evaluate. That's error, the only state that means something is wrong with the alert itself. Thursday, the data is clean again. 2 nulls, condition false, back to okay. 3 states. Okay, the data is fine. Triggered, the data crossed your line.